Good afternoon, everybody. I'm thrilled to be here today. My name is Steve DeCina. I'm the Executive Director of the Office of Vice Provost for Climate Science, Policy, and Action, or what we call Penn Climate for short. And it is my pleasure to introduce our Jisung Park, Professor Park, for the second installment of the Penn Climate Seminar today. Professor Park is an assistant professor at SP2 and holds a secondary appointment at Wharton. In the many conversations I have had with Professor Park since I came here, he has reiterated to me that when you align your work with social value creation and to meet a true need, good things happen. And you'll see his work exemplifies that. And every conversation I've had with him since I've been here, I have left inspired. So I think you will all probably leave very inspired today as well. Professor Park's research examines how environmental factors shape economic opportunities and human well-being, work that is essential for combating climate change and facing our climate challenges. His research on the relationship between heat and learning is very impactful. Especially, he's analyzed millions of test scores to reveal how physical learning environments contribute to educational achievement gaps and economic inequality, right? Something that we have been talking a lot about lately. He's also explored how heat affects labor markets and how environmental change and disasters impact workers and businesses. Professor Park received his PhD in economics from Harvard. He holds master's degrees from Oxford in environmental change and management and development economics, and he has published in countless high-impact journals. He's frequently featured on national and international media sources like NPR and the New York Times, and media in South Korea and other places as well. Outside of academia, Professor Park has advised governments, policymakers worldwide. And on a personal level, I'm really looking forward to this talk. You know, my work at the EPA, I looked at vulnerable communities and how adverse environments, especially air quality, affected them. And also just teaching in Newark, New Jersey for as long as I did. You know, I saw the things that my students were going through and how much environment impacted them. And so without further ado, I'd like to welcome Professor Park to give his seminar today.
Thank you so much for that overly generous and kind introduction. I think inspired is a high bar. I've only got room to go down from there. So thanks for setting a bar I cannot meet. But in all seriousness, thank you for setting this up, Steve, Michael Mann, and others at Penn Climate for setting up this seminar series, all of you for being here. Once again, my name is Jisung Park. I am an environmental economist, and one of the things that means is that I'm used to getting questions throughout the seminar. I know we only have an hour. I have a whole slide deck prepared, but comprehensiveness of coverage is not as important as the quality of our engagement, so please feel free to ask questions throughout. I will hold the speaker's prerogative to skip ahead if we're really running short on time, though. What I'd like to try to do today is just share a few observations and insights and perspectives from research that my colleagues and I have been doing, as well as others in my field, that might, I hope, one, encourage us to think about climate change through a slightly different lens and thinking more about the sort of everyday impacts as opposed to the eventual potential catastrophe. And then two, maybe think about how these data points might serve as inputs to important decisions, particularly policy decisions, both about mitigating climate change in the long run, as well as adapting to the effects of climate change in the short to medium run. So that's sort of the intention. Let me start, however, with a short story and an example in the context of wildfires. So I think we all are familiar with the idea that wildfires can be devastating when and where they occur. One of the most actually viscerally frightening experience for my wife and me when we moved to Los Angeles. My first job out of the PhD in economics was at UCLA. Was actually the week we moved into our apartment. This was the Skirball fire of 2017, and the mandatory evacuation order came just about a mile from our apartment. And this was right in the process where, as we were unpacking our boxes, and I still remember looking at my wife and saying, should we be repacking and going somewhere else? As we know, fires can be very devastating, especially for communities that are directly affected by them. But a question I want to pose is how mindful are we on a day-to-day basis of the everyday health and productivity consequences of the smoke. So here's what I mean. If you look at official statistics, since 2005, the flames from wildfires are responsible for, have been held, are responsible for anywhere between 20 and 30 mortality events, casualties per year in the United States. So we all may recall the fires in Los Angeles earlier this year, devastating wildfires. Actually, many of my former UCLA colleagues have friends and family who lost their homes in these fires, and they're still rebuilding. That fire has 12 confirmed casualties. But according to recent research by Marshall Burke and others at Stanford and elsewhere, the downwind smoke from these wildfires may have been responsible for anywhere between 5, and 15,000 additional deaths, right? Excess mortality, deaths per year in the United States because of the cumulative consequences of poor air quality associated with downwind wildfire smoke. And as you can see from this photo, and as we know, wildfire smoke from the US West can travel great distances even to Canada and the East Coast. I think many of us who live on the East Coast experienced a particularly acute version of this a couple of summers ago. This is a picture of Manhattan from June 2023, when wildfires in Canada blew smoke down our way. You have these eerie red skies. The air quality index, which is a composite index of various sources of air pollution, not limited to PM, which particulate matter, which is what typically comprises wildfire smoke. But the air quality index in Manhattan on June 3rd, 2023 was over 300, which made it one of the most polluted, if not the most polluted city air quality-wise on the planet that day. But what I want to, what I'd like to draw our attention to is the fact that these kinds of extreme acute events, while they may be more psychologically salient from a cumulative sort of economic welfare impact perspective, they may be, how do we put this? They may not be the only thing that matters, right? So if you actually look at the data, most polluted days that, according to the research, have adverse health and productivity consequences, so days with air quality index in the 50 to 100 range, for example, they're nowhere near as visibly salient, but they're much more numerous and potentially more cumulatively damaging. So I guess if I had to state two sort of high-level observations that have been really guiding much of my own work in this area so far, the first is that climate hazards vary in their psychological salience, right? You have what you might call, and of course this is, it's a spectrum, not a binary, but one could place in one bucket the salient climate hazards, the wildfire flames, the hurricanes, the mega storms, the floods, the extreme heat waves, and the more subtle climate hazards. And here I would categorize wildfire smoke as a subtle climate hazard, and also subtle changes in temperature distribution. So more days in the 80s and 90s Fahrenheit, for instance. These subtle shifts, one might argue, are important components of climate risk that may not be as psychologically salient. The second observation is that the effects of climate hazards, right, of all kinds, and let's just limit it to the effects on human outcomes, right, human health and economic outcomes, are not limited to physical capital destruction, right, the destruction of bridges, factories, homes, etc., but may also include human capital, what economists call human capital destruction. This could be in the form of lost productivity. It could be in the form of increased mortality and morbidity, more ER visits, fewer outdoor yoga sessions, less exercise outdoors, all the things that really make up our quality of life. How might these factors be affected by climate hazards of various kinds? So really, if I had to sum up much of the work that I'm about to present to you today, it's sort of aimed at trying to answer this question. To what extent might the less psychologically salient consequences of climate change, including the subtle effects, as I'm about to show you in a minute, of hotter temperature, and how they might affect human capital be relevant for economic decision making. So that's really been the guiding principle behind much of the work that I've done so far. So here's the aspirational roadmap. Again, we don't need to cover anything, so if you have any questions at any point, please feel free to chime in. But I'd like to spend a little bit of time talking through some earlier work on how hotter temperature affects human performance. I'll focus in particular on some of the work that Steve alluded to in the context of temperature and test performance and learning. And then I'd like to move on and talk about some ongoing research with actually a few colleagues that are in the room here today as well, on how temperature might affect working conditions, excuse me, inequality in working conditions, and how workers and firms may or may not adapt to changes in working conditions that arise from climate change. And then if we have time, I'd love to spend just a few minutes talking about what all of this might mean for policy, particularly around adaptation and resilience policy. Before I move on, I'd be remiss if I didn't mention that research is a team sport, and most of the work that I'm about to share with you would not have been possible without hours and hours and hours of meetings, analysis, and collaborative work with the folks you see on the screen, as well as many others. I'd like to acknowledge our postdoc, Paul Stienier, who's in the back over there, and a PhD student, Hussel Seal, who's here as well. But Patrick Baer, Anna Stansbury, Nora Pankratz, and Josh Goodman are also co-authors on much of the work that I'm about to show you. But first, let's, level set a little bit, just in terms of where things stand on the climate. I assume that you're here during Climate Week. All of us have some sort of baseline understanding of climate change as an issue. I'm probably telling you things you already know when I mention the fact that the world has warmed a considerable amount already, by some estimates already 1.3, 1.4 degrees above pre-industrial averages at this point. And look, not to be a pessimist, but maybe just to be a realist, the fact of the matter is that given the half-life of CO2 in the atmosphere, which is around 30, 35 years, right, we've baked a lot of warming into the system, right? Even if we were to wave a magic wand and somehow magically reduce or completely eliminate global greenhouse gas emissions tomorrow, because of the inertial properties of the climate system, there would be at least a few decades of considerable residual warming, right, that we can expect moving forward. That isn't to say that over the long run, we cannot and should not curtail the path of warming, right, on the 2060, 2070 plus horizon. But it's worth bearing in mind that at this point, there is a considerable amount of warming that we will need to live with, and we will need to find ways to adapt to, at least over the next 20 to 30 years. Again, when we have time at the end of this seminar, I would love to talk about what the evidence so far suggests in terms of the optimal amount of mitigation that we should be engaging in. Mitigation, by mitigation, I mean emissions reductions to, right, curb the amount of total warming. But this is just a fact worth noting. If you're anything like me, I find it a little bit challenging to conceptualize intuitively what 1.5 degrees Celsius, 2 degrees Celsius of global average mean temperature, global mean temperature increase means. One way to think about it is what the change in annual average temperature globally manifests as in terms of the number of particularly hot days locally. So I'm going to draw an artificial threshold at 90 degrees Fahrenheit, count the number of days above that threshold. By that measure, with sort of anywhere between 1.5 and 2 degrees Celsius of global average warming, we can expect places like Montreal to experience roughly 5 additional days per year above 90 degrees Fahrenheit. But as you move closer to the equator, and there are other factors that matter as well, places like Atlanta or Greece, we may be talking about a couple dozen additional days per year above 90. And in places like Bangkok, Thailand, or in Ghana, for instance, we may see on the order of 100 additional days per year where high temperatures reach above 90 degrees Fahrenheit, on top of what is already experienced in these places. So that's one way to think about how even so-called non-catastrophic warming may manifest locally in terms of hotter temperature. Okay, so that begs the question, well, what does hotter temperature mean for the outcomes that we care about, including human productivity? Turns out we're not the first to explore this question. Question has been of interest for a very long time, including dating back to pre-World War II studies by the British Navy, where naval officers were put into a room where temperature was experimentally varied. They also were asked to wear thermometers in very uncomfortable places. I won't tell you where exactly they had to wear them. But in this experimental setting, temperature was varied, and they were asked to engage in a series of cognitive and physical tasks, things like interpreting Morse code, and they counted the number of errors that were made, right, during this time. And these and other studies that have mimicked them find this sort of consistent inverted U-shaped relationship between experienced indoor temperature and human task productivity on a wide range of tasks. Now, this is consistent with what we understand in terms of human physiology about how both hot and cold temperatures can affect our brain and other physiological processes. And these experiments have clear strengths, right? I mean, you're experimentally varying temperature, and so causality, you have that down pretty strongly, right? The strength is internal validity. We know pretty confidently that the thing that is varying here is temperature. The thing that is causing the change in performance is temperature. I think the biggest weakness of these kind of laboratory experiments, as with many laboratory experiments, is that it's harder to generalize from those laboratory settings. Okay, what does hotter temperature in the economy, in the world at large, actually mean for economic outcomes that we care about? And this may be because there's heterogeneity in the way that heat affects different individuals, by age, by gender, etc. It may be because in the real world, the stakes are higher, maybe on a job interview or on a work site where your wages depend on your exertion of labor and the acuity with which you do it. Maybe the effect is reduced. Or maybe we're not able to account for the various adaptations that human beings can engage in, whether it's technological, process-oriented, or et cetera. All of these pieces may be important in answering the broader question of what does climate change mean, right, for society at large. And so I take these laboratory experiments as suggestive, but they're incomplete. Another way to approach this might be to look more anecdotally, looking at cross-sectional data. And in fact, if you look at writing of philosophers dating back to Aristotle and Montesquieu, the casual observation has often been made that hotter places do not seem to be conducive to human flourishing. Now, I won't go into the very dangerous assertions that have been made based on similar claims of that sort. But just to say that there is a very strong correlation in the cross-section between hotter places and poorer places. This is plotting per capita income on the y-axis by country and annual average temperature on the x-axis. And you can see, I think the slope of that line is something like 8% per degree Celsius. This actually holds within countries. This is looking at counties within the United States. But before I get ahead of myself, I'm sure alarm bells are going off in everyone's mind. Correlation is not causation. In fact, this kind of cross-sectional regression is probably the mother of all omitted variable bias problems, right? I mean, there's so many things, right, that could be correlated with average temperature that may determine average income, right? And so we may be misattributing the differences in income, right? Nigeria, which is much hotter and poorer than Norway, right, may be poorer for reasons that have nothing to do with its hotness, right? And we probably don't have time to go through the list because the list is so long. So while the strength, I guess, if you want to even be so generous to call this an analysis, the strength of this kind of casual correlation is that we're using real economic indicators that we care a lot about, GDP in this case. But the weakness is that the evidence is circumstantial at best, and there may be many other omitted variables that are driving this relationship. Okay, so to maybe perhaps to crudely summarize a by now huge literature on this subject, I'd point to two sort of innovations that have allowed us to improve on both of those approaches that I've argued are limited in their own ways. The first is that we've, as researchers, we've used we now use panel variation, that is variation in temperature within a given country over time, within a given county over time, within a given individual's life course over time, in using data from settings that are arguably economically more relevant than the laboratory settings that I described to you earlier. And so combining these two features, one can argue that we're able to tell a more causally robust story, but using data and outcomes that are arguably more economically relevant to the question at hand being, what might some of the implications of climate change be, hotter temperature from climate change be for economic outcomes? With me so far? Okay. So let me just share a couple of snapshots from some studies that I and others have done in this space, looking at extending the work on heat and temperature and performance in the lab to higher stakes settings, notably in the context of education. So in my job market paper, I was able to use data from the New York City Public School District, linking individual level test scores to local daily weather data for over 1,000 schools in the New York City public school system, to look at how the temperature on the day of an important exam. Anyone here from New York City? Did you take the Regents exams when you were in high school? Yeah, so these are the exams that you take roughly in June each year, right? Yep, they're spread out over the course of anywhere between 1 to 2 weeks, right? And for most students, these are important exams. In fact, for the median New York City public school student who's on the sort of pass-fail margin on many classes, passing enough of these exams can mean the difference between getting a high school diploma or not, being able to apply to college, to CUNYs or not, for instance. And so I'm going to skip, for now, the econometric estimation equation. I'll show you the estimation equation for the other studies that we're working on. But in the interest of time, let me just note the intuition behind the study, which is that we're just leveraging the fact that we know when and where exams are taken for each student, for each subject. We have multiple test takes per student. And so we can exploit the fact that on any given test day or test time, really, we know when the tests were taken. There's quite a bit of variation both across schools and across time in terms of the temperature environment the student faced. And because these tests actually are administered by the New York State and the location and timing of the exam are set way in advance, there's less of a concern for selection into the timing and location of the test that might bias our results. And so exploiting this kind of day-to-day variation in temperature across different test takes and times, I find that the temperature that a student experiences during the exam, so the ambient conditions outside of the school, appear to have a causal impact on their performance on the exam. So if you're unfortunate enough to take your Regents exam on a 90-degree day, in our data, the effect is roughly a 14% of a standard deviation decline in performance relative to your own average. That translates for the average New York City public school student into a roughly 10% reduction in the chance of passing a given subject. Yeah.
So, but the schools have air conditioning or not?
That is a great question. I tried really hard to find data on school level air conditioning. It was not easy to find. It wasn't complete. The best available evidence that I could find was from building condition assessment reports. And the short answer is not all schools have air conditioning. Even the ones that do, the state of repair or disrepair varies quite a bit. And so estimates vary, but again, based on the building condition assessment reports, my guess was that between 50 and 70% of classrooms had functional air conditioning at this time. Yeah. So this plot is showing that relationship. Each of these dots, it's a bin scatter plot. So each of those dots is roughly 40,000 test scores. The upshot of all this is that taking an exam on a hot day in New York City not only has measurable effects on your test day performance, but because these exams, again, are so economically meaningful for the students, they actually affect your probability of graduating from high school on time or at all, because we can trace these students' graduation status using the data. In the interest of time, I'm going to move on, but just to note that Josh Graf-Zivin and his colleagues find very similar effects roughly similar magnitudes in arguably more high-stakes exams in the context of Chinese college entrance exams, where temperature appears to reduce performance by roughly the same magnitude as well. Interesting tidbit about adaptation and potential constraints to adaptation. Again, don't have time to go into the details. That's not a normal distribution of scores. That's the distribution of scores in the New York in the test score data that I have. The pass-fail thresholds are here and here. So other papers have actually shown that New York City public school teachers were engaging in discretionary grade manipulation. So basically, when students were scoring 64, 63, they were finding ways to give more partial credit so that they become a 65, 66. I'm not the first to show that, actually, but what I show in this paper is that the rate at which teachers appear to be bumping up, sort of giving students a little bit of a grade boost, very systematically with the temperature in the testing environment. So one way to interpret this, I have no way to verify this, but one way to interpret this is that in a constrained environment, teachers are sort of trying to minimize the long-term harm that is done, right, by this idiosyncratic weather shock, which is a hot temperature environment on an important test day. Don't want to make too much of this, but it's worth noting that there are actually sustainability ordinances in New York City that inhibited teachers from installing, if they wanted to install window units in their classroom, for instance, they actually are not allowed to do that because of other rules. So this is just sort of, in my mind, indicative of potential administrative or other barriers to adaptation that we might want to think about. But again, no real proof here, just suggestive evidence. I'm gonna do it on time. Okay. Being unlucky enough to take an important exam on a hot day is one thing, but being exposed to hotter temperature over time and having that actually reduce the amount of learning you accomplish over your educational career is a different thing, right? And so to test that latter question, Josh Goodman, Mike Hurwitz, John Smith, and I, we teamed up with College Board, who graciously allowed us to access anonymized PSAT records. Many of us are actually probably in this data set. This is a universe of PSAT scores in the United States over a roughly 15-year period, as well as to conduct what was at the time the first nationwide survey of school air conditioning status. It turns out there was no centralized database of whether or not schools and classrooms had air conditioning. So again, skipping ahead, skipping a lot of hard work and methods, but just noting that we're using similar methods here. Instead of test day temperature, now we're looking at how changes in the cumulative amount of heat you experience during school days in an academic year, how that variation affects the variation in how much you learn between test takes. So leveraging the fact that many students took the PSAT multiple times, we're looking at how we're trying to ask the question, how does the heat you experience in the classroom affect the rate of learning as evidenced by standardized score improvements? Yes, question.
That the high heat might have closed the school early, say, so they lost a half a day at instruction.
It's a great question. We're unfortunately not able to say much about mechanisms. We're just going to infer, we're just going to try to say, this is the amount of heat you experienced. This is the rate of learning loss that you experience as a consequence of that. Now, we do differentiate between heat experienced during summer, school year, weekends versus weekdays during the school year. And in fact, let me tell you the main effect first, and then let me tell you about that in a minute. But we're not actually able to differentiate why whatever we show is happening. But what we show in this paper is that students who experience a 1 degree Fahrenheit hotter than average school year appear to learn roughly 1% less or more slowly than they otherwise would have. It's a subtle effect, but it's a highly heterogeneous effect. The effect is multiple times that for racial minorities and for low-income students. The effect loads primarily, to kind of get to your question, on weekdays during the school year. So it's suggestive of the idea that it might be something having to do with actual learning in the classroom as opposed to something else, but not definitive. And we also provide some suggestive evidence that school air conditioning may be able to greatly offset this effect. Now, caveat, we don't have randomized treatment of air conditioning. It's not as if we're able to vary experimentally the amount of air conditioning that students experience. We do, however, have reported changes in the amount of air conditioning that schools report to have had 10 years prior to the survey and then at the time of the survey. So we can leverage that to at least give us some signal as to whether school air conditioning is protective. And according to that analysis, if a school has 100% AC, this effect is cut roughly into a quarter, right? Again, in the interest of time, I'll be brief, but we follow up that study with a study using similar methods, different data, standardized test scores from roughly 68 different countries, including the US, but also other countries you see on the map here. And we find very similar effects of hotter temperature during school years leading up to an important exam, reducing the performance on that subsequent exam. In fact, the magnitudes are significantly larger in many parts of the world that are hotter and poorer than the United States. I'll actually pause here for questions before I move on to talking about workers. Yeah. I have not. That's a great question. Would you mind expanding a little bit as to what you have in mind?
Those are the most problematic as far as I'm aware of survivability.
Right. In terms of survivability, absolutely. If I may try to summarize, there's a long-standing question between, is it the heat? Is it the humidity? Is it some combination? Wet bulb globe temperature is a way to attempt to measure humidity inclusive experienced temperature, right? What I've been showing you is mostly dry bulb temperature. There are many reasons for that. It turns out that measuring wet bulb globe temperature is not easy. Inferring it based on precipitation readings and temperature readings is not impossible. We've tried that. But two, when we've tried to run a horse race between wet bulb temperature and dry bulb temperature, when we have the data, it doesn't appear to be significantly different. But that could just be an artifact of our setting. We know from other settings that high humidity certainly can make the experience worse. Yeah, absolutely. Other questions? Okay, so that's the evidence on how heat might affect human task productivity, performance, and learning. Now let me switch gears and talk a little bit about our work on heat and working conditions. Why might this be an issue? Many reasons, starting with the fact that if you look across the world, there are actually many millions, actually over 1 billion individuals whose primary occupation exposes them regularly to harsh environmental conditions. There are over 1 billion agricultural workers globally, for instance. There are almost 200 million construction workers. And there are actually many tens of millions of other workers, which, as you'll see, who work in sort of industries that are ostensibly protected from the elements. They don't occur primarily outdoors, but appear to be sort of at risk or affected by changes in ambient environmental conditions nevertheless. So in sectors like manufacturing, warehousing, et cetera. It's also worth reminding us of the very basic fact that most working age adults spend most working age adults spend most of their waking hours at work, and most working age adults earn most of their income from working. I think it's easy for us in this room to forget that even in the United States, which is one of the wealthiest economies in the world, there is a wide swath of workers, especially among the 100 million or so American workers without a bachelor's degree, who appear to experience routine exposure to harsh environmental conditions on the job. So according to a recent survey, right, over 2/3 of American workers without a bachelor's degree report routine exposure to harsh environmental conditions, including extreme temperatures at work. So exposure to heat as well as other climatic hazards on the job may be of potential significance. We have tried to look at this through the particular prism of how hotter temperature or temperature generally might affect workplace safety. So we're leveraging a pretty cool data set that we have available thanks to the California Department of Industrial Relations, where we have the universe of all workers' compensation insurance claims. So anytime a workers' comp claim is filed, that goes into this database. We have, among other things, information on the zip code of the work site, separately from the zip code of the residence of the worker. And importantly for our analysis, we have the date and location of the injury itself, which enables us to, again, getting back to the methods, line up the data in such a way that, right, we can make it as if nature herself has run a series of experiments that would otherwise be wholly unethical to run, which is to expose workers in dangerous conditions to potentially more dangerous heat. There's a lot of other information. It's a very rich data set. We're going to leverage some of this. But the basic question of interest is, how does temperature affect workplace safety? That's the first question. I'll get to some of the others in a minute. So we're linking those individual insurance claims to daily weather data from the PRISM model. Again, we're going to be using dry bulb daily min, max, and mean temperature. I'm going to focus on the results that use daily max temperature. All the results I'll show you have controls for daily precipitation in there as well. And for those of us who are interested in the econometrics, this is the estimation equation. If you're not interested in this, you can just earmuff for 2 minutes. We're basically regressing the count of injuries in a given zip code I, day D, month M, and year Y on a vector of temperature bins. So instead of specifying a functional form, we're just going to let the data tell us, right, what is the relationship between different temperature levels, daily temperature levels, and injury counts, as well as daily precipitation bins. But really the main action, I guess, in terms of getting at causality comes from these two fixed effects. It's the zip code month fixed effect, which is essentially allowing us to look at daily variation in temperature within a given zip code and controlling for that zip code specific seasonality, right? Because you might imagine that, pace of work, demand for products may vary by zip code in California. It may also vary by month. There's Amazon Prime Day, and so maybe there's more, right, of a rush for packaging. We're going to try to control for that flexibly by using the zip code month effect, fixed effect. We're also going to have a month-year fixed effect, which is essentially controlling for, shocks, global shocks that are economy-wide to California that occur at the monthly level. So we're actually not are we including? We may be including a little bit of the pandemic, but right, March of 2020 is a global shock that you would see in this data. We're going to try to control for that with the month-year fixed effect. Okay, those of you who had earmuffs on, you can take them back off. Basically, we are trying to come as close as possible to estimating the causal effect of daily temperature on daily injuries, acknowledging the fact that, again, if you just were to look at the cross-section without these controls, temperature might be correlated with injury rates for all kinds of reasons, right, that you want to control for. So this is sort of the first main result. This is showing us the effect of having a daily temperature in any one of daily maximum temperature in any one of these temperature bins on injuries in a given zip code on a given day. 95% confidence intervals plotted. And as you can see, right, interestingly, the sort of optimal zone in terms of the sort of workplace safety minimizing temperature appears to be perhaps slightly lower than the optimal zone you saw for task productivity in the lab, and who knows why that is. It's hard to say because standard errors are much larger here. But the basic point I'd like to stress is that, right, hotter temperature appears to be bad for workplace safety, right? The magnitude here is non-trivial. If you're working on a 90, 95 degree day, it's a roughly 5 to 9% increase in injuries of all kinds. 100-degree day plus is a much larger effect. Perhaps not surprisingly, the effect is largest in sectors like agriculture or construction, where the majority of work occurs outdoors. But somewhat surprisingly, at least for me, was the fact that we still observe a statistically significant and economically meaningful effect of hotter temperature in industries like manufacturing, in some wholesale, retail, and warehousing related sectors, as well as in some retail and entertainment, food service, and accommodation. Another point that the data allows us to get at, which I think is important from a policy perspective, is this notion of whether we should be focusing on heat illnesses or something else. Now, you see a lot of writing in the media and in policy documents about heat illnesses as being an important concern. This is anecdotal, but according to my conversations with folks, with physicians as well as folks who are in the field trying to measure this stuff, actually determining whether a particular incident is a heat illness is actually apparently quite difficult for a physician to do definitively. And so maybe not inconsistent with that, we find that, okay, there are some claims in our data that are explicitly tagged as being due to extreme temperature, heat illnesses, burns, etc. These things spike, right, on hot days. But if you actually look at it, the vast majority of the overall increase in claims comes from all other types of injuries and illnesses. So someone, falling off of a ladder, someone dropping a hazardous substance on themselves, someone being struck by a moving vehicle. Because even though the marginal effect of a hot day is smaller for these all other causes, but the base upon which that marginal effect occurs is so much larger, it's actually the case that this effect dominates this other one in terms of the total number of workers that are affected. Does that make sense? So in other words, heat illnesses, the medically determined heat illnesses, appear to be a smaller piece of the overall pie when it comes to the cumulative consequence of heat on workplace safety. Yeah, Michael.
Referring to cardiovascular or stroke, those sorts of events that can be increased in prevalence by heat, or something else?
Something else. I'm referring explicitly to when the doctor says this is a heat stroke. And that is different from if you had a heart attack and they list a secondary potential cause as heat, among others. And they don't do that very often. But yeah, these all others are including those kinds of injuries. I blew out my back, I sprained my arm. Yeah. I don't know if you can sprain an arm. You sprain your wrist. Yeah. Yeah, these are technically including long-term illnesses. I will note that the workers' comp system, again, qualitatively is probably not doing the best job at capturing long-term illnesses. And so that might be a part of the data that is underrepresented. But certainly there's some epidemiological evidence to suggest that long-term heat exposure can exacerbate longer-term illnesses like chronic kidney disease, et cetera, right? Is that what you had in mind? Okay. Yeah, so again, in terms of magnitude, I just want to stress, if you look at official statistics, Cal OSHA, for instance, puts out the number of heat illnesses, right, according to their data, at around 60 heat illnesses in California per year. One can disagree about how you estimate the additional workplace injury burden associated with heat. You have to pick a counterfactual, and we pick a baseline where we assume everyone had perfectly air-conditioned work environments. How many fewer injuries would we see given our data? And our estimate is that roughly 15,000 workplace injuries and illnesses are at least proximally caused by hotter temperature on the job. So just to give us a sense of the rough magnitude of how these things compare. Okay. How am I doing on time? We've got 12-ish minutes. So then, if you'll permit me, let me just share one more ongoing study that Paul and others and I are engaging in, which is really trying to think about determinants of adaptation on the job. So if maybe we are convinced that heat and other climate hazards on the job may be important for worker well-being, potentially for productivity, we might want to think about, well, what are the determinants of adaptation, right? What is prohibiting workers and firms from engaging in activities that might protect them from the elements? Is it even possible, right, to protect ourselves from these effects? And it's just, I guess, to take a step back, the way economists think about this is to note that anytime you're talking about the workplace, you're talking about a two-way transaction where the firm is purchasing labor as an input to their production process. And the worker is also purchasing or negotiating a compensation package that includes not only the wage that they're paid, but also the working conditions that they experience. And so part of that bundle of working conditions may include protection from climate hazards, right? Adaptation to climate change. And, I'm not an engineer, but I imagine there are many different ways that a firm and an employee could potentially try to reduce the harm, both to productivity and to worker safety and health, from something like heat. Maybe you install shade structures, you take the night shift, you have shorter shifts, maybe you install air conditioning. There are actually cooling vests that you might wear. We're going to be agnostic as to what mechanism, but the idea that we have in mind is, well, in a competitive labor market, you would expect firms and workers to invest in adaptation to the point where the marginal cost of doing so is roughly equal to the marginal benefit of doing so. Okay, so that's all in good. I guess the hypothesis we're trying to test in this paper is that the structure of the labor market might matter when it comes to how much adaptation takes place and what kind of adaptation takes place. And again, the bigger picture question we're interested in is, will workers and firms adapt to climate change? What are the potential barriers to adaptation? What is the role, really, of government, if any, in facilitating adaptation? So in theory, you might expect that workers and employers reach perfectly competitive, efficient bargaining outcomes, and you find the perfect mix of shade, shorter shifts, air conditioning, et cetera, that minimizes these effects, right, at the lowest cost. But you may also believe that we live in a world where the alignment of incentives is less than complete. Maybe when a worker gets injured, some of the healthcare costs are externalized to the firm, that is not borne completely by the worker and the firm. Or maybe there are asymmetries in the kind of information that the worker has access to in terms of what constitutes a safe workplace versus what the employer has access to. In either of these scenarios, you would expect that the relative bargaining position of the worker, that is how much voice the worker has, or how much voice the worker has in that employment relationship, may matter in terms of how much protection from the elements, how much what we're calling climate adaptation is actually engaged in. And so we try to look at this using a very cool data set that Anna Stansbury and her colleagues at MIT put together, where we're basically able to see how workers realized outside job options, which we're going to use as a proxy for their bargaining position, change over time. So in other words, we're able to, suppose we have a measure of the kinds of jobs that landscapers typically transition to if they were to leave landscaping. And this is based on millions of resumes, right? And suppose we knew how wages were changing in all of these jobs that landscapers typically go to. So the wages of physicians probably doesn't matter for landscapers, but the wages of meatpacking plant service workers or construction work may matter for landscapers. And so for every local occupational labor market in California, for roughly 17,000 city occupation level labor markets, we're actually going to look at, okay, how does the level of climate adaptation on the job, which we're going to measure in terms of the temperature injury relationship that I showed you before, the slope of that relationship, right? On a hot day, how many more injuries occur? How does that object vary based on workers' relative bargaining position, which we're going to try to measure using this measure of changing outside option wages. Okay? And again, I'd be happy to answer questions about the methodology during the Q&A if we have time, but the punchline, at least the evolving punchline, it's still an ongoing project, is that better outside options, i.e. when workers have better relative bargaining power, they appear to be able to negotiate for safer working conditions generally and more protection from the heat in particular. This is showing us, so instead of all of those temperature bins, now we've just collapsed it into 3 different bins: days below 50, days between 50 and 90, days above 90 degrees Fahrenheit. And what I'd like us to focus on is the fact that, okay, right, the average worker experiences a roughly 8% increase in injuries on a 90-degree day. But depending on the relative bargaining power, depending on this outside option wage measure that I just described, albeit in a somewhat rushed manner, depending on where you are in that distribution, the effect of heat on injuries can be much larger or it can be much smaller. In fact, right, a 1 standard deviation increase in your relative bargaining position in our data is associated with a roughly 30 to 40%, 30 to 45% reduction in the heat sensitivity of injuries. So one way to interpret this, right, is that yes, there appear to be many ways in which workers and firms can reduce the effects of heat on workplace injuries and illnesses, but some of it may depend on the extent to which the incentives between workers and employers are in fact aligned to do so, because some of these improvements may be productivity enhancing as well as worker health enhancing, and some of these may not be as productivity enhancing and health enhancing. We can't tell that for sure, but we at least are providing some evidence consistent with the idea that, again, the incentive structure and the bargaining position might matter. Okay, so I've left 4 minutes for discussion. We asked a few questions throughout, so I'm going to give myself a little bit of a pass on the Q&A part. Please ask questions now if you have them. But let me just briefly say, just to zoom out while I have a chance. I see this work as being consistent with a broader, really a literature that has really exploded in recent years, which shows that even moderately elevated temperature, days in the 80s and 90s Fahrenheit, which we don't really consider to be an extreme heat wave, right, appears to have significant adverse consequences for such outcomes as labor productivity, student test scores, ER visits, mental health, even the amount of local crime and the amount of profanity on one's Twitter feed actually varies systematically with the temperature and in such a direction that hotter temperature leads to more negative outcomes. You know, I don't know if Novak Djokovic suffers from this per se, but professional tennis players actually engage in more double faults when the temperature is above 90 degrees Fahrenheit. So it's all consistent with this broader story that is emerging, which is that even moderately elevated temperature and similarly to the the moderately elevated air quality index levels can have sort of subtle but cumulatively potentially damaging consequences for human activity, which in my mind begs an important question. One, about what are we measuring the total consequences of future climate change correctly, and how does that inform how we think about the stringency of greenhouse gas reductions that we should engage in today? And the short answer, at least in my read of the literature, is that the integrated assessment models currently do not capture many of these effects, or at least not completely. But it also opens up a set of really important and I'd argue just as urgent questions around, are there adaptation policies that we should be engaging in that are important or necessary to overcome frictions or barriers in the process of adapting to the climate change, to the increase in smoke exposure, to the increase in heat exposure, to sea level rise, et cetera, that we may see. And those interventions may be in the form of correcting market failures, but they may also be in the form of correcting government failures, right, in terms of policies that are inhibiting more efficient adaptation. So that's the big picture. I'd love to take questions.